हाँ आ गया. Is it coming? Okay, so we are going to look at change of basis. So let us look at a problem. The problem is, suppose you are given two bases, beta 1 and beta 2, of a finite dimensional vector space V, and suppose small v be any vector, and alpha, which is alpha 1 to alpha n, and beta 1 to beta n, be two coordinates, with the coordinates of v with respect to basis beta 1 and beta 2. The question is, how are these alpha and beta related? The coordinates of v with respect to two bases, how they are related? I'm sure all of you must have studied this. They are related by a matrix called transition matrix. So let us look at how we can do this in Sage. So let us start with, suppose I have n equal to 5 dimensional vector space, and let us say V is vector space over Q of dimension 5. Okay, this is the vector space, and you want to have two bases, beta 1 beta 2, arbitrary basis. So of course you can generate 5 linearly independent vectors. So let us generate b1 as a random set of 5 vectors. So how do I generate that? So we will start a list. We'll say that v dot random element, and how many such element? 5 of them. So we'll say for i in range n, that is b1. If you want, we will show what is b1. So these are the 5 random vectors. Let us check whether this is a basis. That means we should check whether this is linearly independent. So how do I check that? So we have to say v dot linear dependence, and linear dependence of b1, and in case this gives you an empty list, will be linearly independent. So that's correct. So this is the first basis. Let us generate another basis. Let me call this as b2, again set of 5 vectors, and let us see what is this b2. So this is again a basis. Let us again check whether this is a basis. So this is, just one second, this is b2. Yeah, so this is also a basis. So I randomly selected 5 vectors in v. They are that it forms a basis. So mostly what you can see is that, I mean, the basis vectors are quite dense in the vector space, right? So now what we want to do, we want to have a random vector. So you can, let me define manually. So we have a vector, let us say over qq. Let us, this vector is 1 2 3 4 5. This is a random vector. We want to find coordinates of v with respect to this basis beta 1 and beta 2, b1 and b2 in this case. So let us call this coordinate with respect to b1 as alpha. So let me define alpha is equal to, how did we find this? We have to say so first we need to define a subspace with b1 as a basis. So let us define that. So first we will say w1 is what? It is v dot subspace with basis b1. Okay, similarly w2 to be the subspace with basis b2. Okay, now what are alpha 1, alpha and beta? So alpha is the coordinates with respect to the basis b1. So we'll have to say w1 dot coordinates with of the vector v. Okay, so let us print what is alpha. Alpha will be a list of coordinates. In last time we checked that this is the coordinates, so alpha 1 times the first element of the basis plus alpha 2 times second element and so on, this should be equal to v. Okay, so this gives you a list of vectors, right? Similarly, let us find beta to be the set of the coordinates of v with respect to basis b2. So that's the beta. Let us again print what is beta. So we have got, this is alpha and beta. It looks quite big rational numbers, but it is, or that's what we have. Okay, now what is that we want to do? We want to check, we want to find out how this alpha and beta are related. Okay, how this alpha and beta are related. Okay, so in this case what we can do is, of course there are various ways of doing this problem, but let us find out what do we mean by alpha is a coordinate with respect to basis b. So in case we look at, let us say, matrix, let us define a column matrix with b1, that is first column is the first vector in b1 and so on. So let me call this as let us say mat b1. This is equal to, similarly, what will be the mat b2? This is the mat column matrix with basis, whose columns are basis vectors of b2. Okay, now what will be alpha? What will be alpha? So alpha, actually, how do you get alpha? If you solve, let us say, mat b1 times x is equal to v, you get alpha. So therefore what we have is, we you can just check that mat times alpha. So alpha, you can see here, alpha is a list. I have to think of that as a vector. So let me define let me call that as vector alpha. This should be equal to v, and that is what you can see here. Similarly, if I say mat b2 times beta, that should also be v, right? So we have now, so what is that? V is equal to mat beta 1 times alpha, which is same as mat beta 2 times beta. Therefore what will be beta? Beta is going to be mat b2 inverse times mat b1. So let us look at mat b2 inverse times mat b1, this times alpha. So mat vector alpha, this should be equal to beta. That, so let us check whether this is equal to beta. Okay, this at present this says false, but I think we have to use boolean of this and then boolean of this. That's true. Okay, so we have verified. So this matrix mat in b2 inverse b1, this is what is called change of basis matrix or transition matrix. Okay, so if you call this as, let us say, m1 is equal to this matrix. So what is m1? M1 is this matrix. Of course it looks quite big, so let me ask it to show, then it will be slightly better looking. Okay, this is a big matrix, 5 cross 5 matrix. So this is a change of basis matrix or transition matrix. Of course you can change that, check that. So what is the relation? M1 times m1 times alpha, the coordinate with respect to beta 1 is equal to the beta, right? You can check m1 inverse for this is true. M1 inverse times vector let us say beta, this would be equal to alpha. This is equal to alpha. Again, you can check boolean of this is equal to this, right? But of course this Sage has found this vector, but manually if you want to use let us say Rref to find this matrix of change of basis, that also you can do. So how will you do? You can see here, for example, this matrix is given by matrix b2 inverse times b1. So what we can do is in b2, in matrix b2 we can append b1 and then apply Rref, and the last 5 columns will give me the transition matrix. So let us try to do that and see how whether we can get the same thing. Okay, so what we will do, so we have mat b2, in that append not append augment mat mat b1, right? So that is this will be 5 rows and 10 columns, and this you apply Rref dot Rref, apply Rref to this, and yeah, so this is Rref. Of course, again it will look quite so now let us call this as AUG. Now let me show AUG. This is a matrix. Now you can see here this last 5 columns is same as this matrix M1, right? So again, we using Rref we are able to find this matrix of change of basis or transition matrix. How do I extract this last 5 columns? So you can use sub matrix. Last time I told you there is an option called sub matrix. So let us say AUG, and then sub matrix, and then you have to say what is the starting row, starting column. So starting row is 0, starting column is 5th column, and then take the remaining. So this is, I can, let me ask it to show. That is the matrix. So you can obtain this matrix using Rref, or you can use inbuilt function to find coordinates, and then again you can find it using matrix inverse. Okay, so this is very simple to find in Sage. Okay, now let us look at, suppose you are given any matrix. Once you are given a matrix, then there are several subspaces associated to that matrix. For example, we can think of columns as vectors, rows also as vectors. So we can take subspace spanned by columns, similarly subspace spanned by rows, right? And you can also look at what is the null space set of all x such that ax equal to 0. That is called the kernel space or null space. So let us see how we can find these subspaces. So let us begin with a matrix. Let us begin with a matrix. So let me just, in case some of you are not aware of this definition, let me say, so generally we call them the 4 fundamental subspaces associated to a matrix. Let us say that if the matrix is M cross N, first is the column space, that is the subspace spanned by the column vectors. Row space, that is the subspace spanned by the rows. And then null space, that is kernel space. And then there is another one called left null space, which is just a null space of A transpose. If A is a linear transformation from Rm to Rn, then A transpose will be linear transformation from Rn to Rm. So these are called 4 fundamental subspaces associated to a given matrix. So let me take a matrix. So for example, let me take reasonably big matrix. So take this. Okay, so this is, let us say this is a matrix A. This is so how many rows? 5 rows and 6 columns. There are 5 rows and 6 columns. Now we want to find what are the column space and row space and null space and left null space. These are what we want to find out. Okay, so of course subspace spanned by rows, we can simply take Rref of A, and whatever the non-zero rows will give me the row space. Similarly, we can take A transpose and then apply Rref, then non-zero rows will give me the column space. And similarly, you can find the take A transpose and find the null space of that will give me left null space. Okay, so how do I find out? So A dot, you can say column space, A dot column space, this will give you the column space. So here in this case it is a vector space of degree 5, that is the number of components, because A is a 5 cross 6 matrix. So therefore it is a it can be thought of as a linear transformation from R6 to R5. And in this case this is a subspace. The column space is a subspace of dimension 3, so 3 vectors, these 3 rows are a basis. It forms a basis of this column space, right? This column space is nothing but image space. So you can simply find A dot row space, A dot row space. So this is again, this is a row space, again this is of dimension 3, this is a dimension 3. Next we can find the kernel. So there is a function called A dot right kernel. Okay, you have to use right because Sage also has left option. So left and right, generally we write A times X. So we write we take vector multiplication on the right side, so that is why this right kernel. Okay, so this is a subspace, again subspace of dimension 3, right? So this is a subspace of R6, in this case Q6, because we have defined matrix over Q rational. So therefore this is a subspace of Q6 and it is of dimension 3. Okay, so again you can see this dimension is 3, dimension of image space is 3, so 3 plus 3 is 6, which is dimension of the domain. So that also verifies this rank nullity theorem. Okay, you could also find, of course you can find rank of this matrix. A dot rank, this is 3, that is dimension of the image space. Okay, then but in case you have to find column space, how will you do? You can take the transpose of the matrix A and then apply Rref and then choose the non-zero rows. Okay, there is also a notion of what is called extended echelon form. So that also gives you all these 4 spaces, right? So of course we have not found yet the left null space. So how will you find this left null space? To find this null space, A will take A dot T, that is A transpose, and then take null space of this, so that right underscore kernel, that will give me left null space, right? So that's the of dimension 2. Now there is, as I said, there is another notion called extended Rref in Sage. So using that also you can find all these things. So if you say A dot extended echelon form, then this is what it gives you. So what it does, to given matrix, it will append an identity matrix. So in this case the matrix is of size 5 cross 6, so it will append 5 by 5 identity matrix and then apply Rref. That is what is called extended echelon form. So let me also put a division. So there is also option called divide or subdivide. I think subdivide is equal to true. Subdivide equal to true. So again you can see here, so you can see here this last bottom right corner, the box contains basis for this left null space. Okay, similarly you can interpret other things. You can maybe look at this Robert Beecher's book. In that there is a section on extended echelon form, so you can look at more concepts related to this. Okay, so yeah, so all these subspaces we are able to find using Rref, and of course there are inbuilt function in this case, right? uh, Sage also has facilities to define matrices over finite field. Okay, so for example, if I want to define a matrix over Z mod 5Z, so that can be defined as GF5. Okay, GF5 stands for Z mod 5Z, this field FP with P equal to 5. Now let us say that we want to define a 3 cross 3 matrix, and the elements are 1, 3, 31. So how will this 31 appear? You have to go modulo 5, whatever is the remainder that will, but let us just say 3. It is 1, 2, 3, 2, 3, 4, 3, 0, 2. And if I ask it to show, this is what you have. So but in case instead of 3, if I say, let us say this is 72, and let us say this 3 is let us say 67. Now if I see what is A, so again you can see here 72 divided by 5, the remainder is 2, so that is what it has come here. Similarly 67 divided by 5, remainder is 2, so again that is 2, right? So you can define matrix over finite field, and again you can find out what is the row space of this, what is column space of this, what is kernel of this. So all these computations can be also done for this kind of matrices which are defined over finite field. Okay, so I mean in fact you can find out the number of elements and all that, etc. We will come to this little later. Okay, similarly you can also define a matrix over polynomial ring. So suppose you want to define a matrix over qx, q box x, right? Set of all polynomials with coefficients coming from rational numbers. So let us say I'll call this as d of x. X is a variable, and then how do I define a matrix? So I'll take a matrix over the domain D and size 3 by 3, and then you mention each first row as some set of 3 polynomials, second row as a set of 3 polynomials, third row is again set of 3 polynomials, right? So that is a matrix over qx, and again you can find row space, column space over this. So in this sense, the Sage has very good facilities to not only just deal with matrices over real numbers or integers or rational numbers, but it can also deal with matrices over finite field, in fact over some polynomial rings and things like that. You can go even more much beyond this. Okay. Right. You can even define matrix over finite field with given generator. So suppose this generator is A, and we want finite field 5 square, and then you can define a matrix over this and find all these again row space, column space, etc. Not only that, you can define vector space over finite field as well. So if I have to define vector space over let us say fp3 of dimension 5, then the option is vector space gf3, that is the field, right? And in case we want to take gf, this is as qq, then we have to say vector space qq5, right? So we had already looked at how to define, let us say, qq5. So this is vector space of dimension 5 over rational field, but in the same thing can be also defined as vector space qq and then comma 5. These two are the same thing. Okay, but as a shortcut we can use qq to the power 5. So here this is vector space over gf3 of dimension 5. Okay, you can even ask for what is the cardinality of this. Let us see what is the cardinality of this set. So it says there are 243. There are 243 elements in this vector space. Of course, you can ask why this is 243. I'm sure you can count the number of elements, right? Not only that, you can even list all the subspaces in that. So that's something which is very nice. So if I say look at v dot subspaces of dimension 1, and then make a list of that, and then count how many are there. So it says that there are 121 subspaces of dimension 1 in this vector space. Okay, so if I ask for what is the dimension 2 subspaces, 1210 subspaces of dimension 2 in this vector space. Of course, you can ask how to count these things, okay, but it has similarly. If I ask for what is dimension 3, that will be again 1221. Dimension 4 will be same as dimension 1, so that will be 121. And you can of course find out basis of this vector space. So by default this is a standard basis. If you want to define, you can define a basis with given set of vectors. All these things can be again done over for a vector space over finite field. So C has very nice facilities to deal with different vector spaces defined over this field of rational numbers or real or complex or even finite field, and over integer rings and things like that. Okay, Sage also has facilities, extensive facilities to generate random matrices. Okay, so for example, if you want to generate a random matrix, 3 cross 3 random matrix over integers, let us say each one varying between minus 10 and 20. So x minus 10 is the beginning, y 20 is the end. So you will get a random matrix starting from minus 10 to 20. All the entries will lie between minus 10 and 20. Okay, so that is, so instead of minus 10, if I say minus 100 to, let us say, 100, everything will lie between minus 100 and 100. Okay, similarly you can define random matrix over Q. Let us say random matrix over Q of size 3 by 4, and in this case you may mention what is the numerator bound, that is what should be the maximum number in the numerator, and denominator bound. Okay, so this is 3 cross 3 matrix. The bound, the numerator will lie between minus 10 and 10, and denominator will also lie between minus 10 and 10. Of course you can have different, let us say I want denominator only between minus 5 and 5, then this will be a random matrix. Okay, so you can generate random matrix. Not only that, you can generate random matrix which is in a clonizable form and of particular rank, right? You can just one second, there is matrix. Random matrix. So this says that you generate a 6 cross 7 random matrix which is in equalizable form and it has a rank 5. Okay, so this kind of thing is very good in case if you are teaching, then this, if you want to generate questions etc of a matrix, generally we take a lot of time to think of such questions, but here you can very easily generate. Similarly, you can generate a matrix which is diagonalizable with given eigenvectors etc. All such facilities are there. So for example, this you can see here, we can generate a 5 cross 5 random matrix over Q which is diagonalizable, and the eigenvalues are 2, 3, minus 1, and 2 is of the eigenvalue 2 is of multiplicity 1, 3 is of multiplicity 2, and minus 1 is of multiplicity 2. Okay, so this kind of thing is also available. Okay, so fine. So whenever we need some random matrix, we can use this. So of course you should take help on random underscore matrix. So you try to take help on underscore random underscore matrix question mark, then, and you can go through this help document. There are many more facilities available when you want to generate random matrices. Okay, right. Now let us move on to how we can define a linear transformation in Sage. So Sage has 4 different ways of defining a linear transformation. The function is linear underscore transformation. So one way to generate is you can give in the matrix of the linear transformation, and you can say whether you want side left or right. Okay, similarly, so by default it will give you side left, but generally we follow side right. We write linear transformation ax as matrix times some vector x is taken on the right side. Similarly, another way of generating a linear transformation, you can give the domain, you can give the codomain and the matrix, or you can simply give the domain, codomain and the function. The function will be suppose f is a linear transform from Rm to Rn, then f image of f will be set of n coordinates. So you have to give as a list. Or you can take linear underscore transformation, you can mention domain, codomain and set of images. Again, the image will be in as a list of uh, images. Okay, so let us take an example. So for example, we want a linear to define a linear transformation T from vector space Q4 to Q4 given by this. So T of x1 is 8x1 plus 8x2 plus 24x3 minus 26x4. T of x1, x2, x3, x4 is 12x1 plus 31x2 plus 96x3 and so on. Right. So this is the first coordinate, second coordinate, third and fourth coordinate. We want to find the various concepts related to T. So for example, once you are given T, what it is image, what is kernel, what is its domain, codomain, what is image of a vector and all such things. Similarly, we can find out matrix of T either with respect to, by default it will give you with respect to standard basis on domain and codomain, but you can have some arbitrary basis on domain and codomain, and with respect to that basis also we can find linear the matrix. And you can also find eigenvalues of that linear transformation. We know how to define eigenvalues and eigenvector of a linear transformation, and in fact you can show that eigenvalue uh, of T is same as eigenvalue of the matrix associated with the linear transformation. But then the question is, in case we look at the matrix depends upon the basis. So if you choose different basis, whether the eigenvalues will be different. The answer is no, the eigenvalues will be the same. That we will also try to verify. So it has a lot of facilities. So let us begin how we can define linear transformation. So first let us say reset means that all the previous things which we have generated will be forgotten. So now let us say m and n. So we want to think of linear transformation from Rm to Rn, or Rn to Rm, whichever you want. So in this case Rn to Rm, and so V is Qq to the power n, W is Qq to the power m. Of course, in this case m and n are same. And now how do we define? So first you need to declare x1, x2, x3, x4 as variables. So these are the variables here, and then define the function f of x1, x2, x3, x4 x4 is equal to the first, this list of the coordinates. The first coordinate is this, second coordinate is this, third coordinate is this, and so on. And this backslash means that you are just breaking the line. In the next line it is shown, otherwise everything will be in single line, which will be difficult to visualize. So that is why this backslash, and then press enter. Okay, so this is so let us execute this. So this we have the image of linear transformation. So we are actually using the third form of this this linear transformation. Okay, now let us see how we are going to define this linear transformation. So what was the definition? You have to say linear transformation. So let us say I'll call this linear transformation as T. T is equal to linear underscore transformation, and domain you have to say. So what is domain? Capital V, the vector space Qn, and then codomain is W Qm, and then the image is given by f. The image is given by f. So that's this is, now you can ask what is T. So it says that T is a vector space morphism, that is homomorphism represented by this matrix. Okay, so this is the matrix, and in this case you can see here the matrix of T. What is the order of this matrix? 4 cross 4 in this case, of course. But this is if you just compare this with what should have been this matrix. Okay, so let me just say, so if you say T dot matrix, by default this matrix is taken as left, so you have to say side is equal to right, RIGST. Okay, this is the matrix, okay, of linear transformation, but this is with respect to standard basis. Okay, so we have not specified what is the basis, so by default it will take standard basis. Okay, now of course you can check what is T of let us say E1. T of E1 should be first column, T of E2 should be second column, T of E3 should be third column. So let us generate let me say E is equal to identity matrix, 4 cross 4 identity matrix, right? So first column is your E1 in this case, so I'll say E1 is equal to E of 0, right? So that is your E1. So now if I say what is T of E1, T of E1, that will be the image of E1, and if you write this as column wise, this should be the first column. Okay, that's correct. Similarly, if I say what is T of E2, so I say E2 is equal to E of 2, sorry, E of 1, and then if I ask for what is T of E2, that will give me T of distance. E2 is not executed. T of E2 is the second column, you can see here, and things like that. Similarly, let me also define E3 to be E of 2 and E4 to be E of 3. So E1, E2, E3 are the standard basis. Okay, now let us say what we can also find out what are the, so for example, if I take a V, a random vector, so let us say vector, some vector, let us say for example 1 3 5 7, okay, and want to find out what is image of T, image of V under T, it gives you the image. You can find out what should be T of, let us say, domain, T domain of T, so that is, we know that it is a Q4. Similarly, we can find out codomain, that is the codomain, again in this case it is a Q4 to Q4, T is from linear transformation from Q4 to Q4, so domain and codomain both are same. You can find out T dot image, T dot image, so this image is, in this case it is 4-dimensional, again you can find the image. You can also find T dot kernel, T dot kernel. So in this case, of course, we can check whether T is injective, is T dot is underscore injective, in this case we know it is, and similarly we can check whether T dot is surjective. Okay, so you can check whether it is injective, surjective, all such things you can do. Of course, you can do this manually also. Next, let us say we want to define matrix of T with respect to given basis. So let us generate some random basis of domain and codomain, and then find out what should be matrix of T with respect to that given basis. Okay, so we can again generate random 4 vectors and check whether this is linearly independent and generate a basis. However, let me define some random 4 vectors. So I have called this as D1, D2, D3, D4, and D as list of D1, D2, D3, D4. Okay, so 4 vectors you could define randomly. Okay, so let us first check whether this forms a basis. So how do I check that? So we'll have to say V dot linear dependence, and of D. We are getting empty set, that means it is linearly dependent. This set is linearly independent, sorry, therefore it forms a basis. Similarly, let us, but then now we want to change the domain to the subspace spanned by this as a basis. So again we will define, let me call this as v1 as a v dot subspace with basis as d. So that is, so now you can see what is v1. v1 is a subspace spanned by these as basis. Okay, similarly let us define a basis on codomain, so that I have called as c1, c2, c3, c4, right, 4 vectors, and c is the list of these 4 vectors. So again we will say w1 as a w dot subspace with basis as c, and so you can again let us see what is w1. Okay, so we have defined subspaces of v and w, we call as v1 and w1 with given basis on domain and codomain. So domain basis is d, codomain basis is c. Okay, now how do I find matrix with respect to this basis? Of course mm, you must have already known how we can do this, right? So you have to simply write, take image of t of c1. So for example you can take t of what is t of d1. This will be a vector in the codomain, and then you find the coordinate of this with respect to the given basis. So I have to simply say w dot coordinates of this with respect to w1. So I have to say w1. Okay, so this will be the first column. This will be the first column. Similarly you can find the other things, or what you can do is you can append image of t d1, t d2, t d3, t d4 onto a column matrix obtained by first column as c1, second column as c2, third column as c3, fourth column as c4, and then apply Rref and extract last 4 columns. Okay, but let us see how we can do this using inbuilt function, then we will verify with that. Okay, or let us first verify with this. So what, let us make a matrix, column matrix whose first column will be c1, second column c2, third column c3, and fourth column c4, and the next column will be t of d1, then t of d2, then t of d3, and then t of d4. Okay, so now what we are going to do, we will apply Rref to this. Okay, and the last 4 column will be the matrix. So let us extract last 4 column of this. So let me call this I don't know, let me say this is my matrix M. This is matrix M. Now so let us extract last 4 columns. How do I extract? M dot, we can use sub matrix, M dot sub matrix starting from 0 through and 4th column. So this is the matrix. Okay, this is the matrix of the linear transformation. So again you can see here the matrix of the linear transformation we can find very easily using Rref, and this students find it very easy to do. Okay. Next, so let us say how we can do this with inbuilt function. So for what you need to do is you need to restrict the domain and codomain to a basis subspace spanned by this basis d and c. So we'll say t dot restrict let me say first domain we will restrict to d, right, and then restrict codomain to c. Okay, and this, let me call this as capital S. Just 1 second. V is a free variable. No, not D. I have to say V1, and this is W1. What happened? Restrict. Oh, the spelling mistake. So codomain. Right, so this is your S. Now you can ask for what is S. S is, it says that this is a vector space morphism represented by by the matrix this, and domain is given by this, codomain is given by this. So it clearly says what exactly this S is. Now let us find matrix of S. S dot matrix with respect to the given basis, and the side is equal to right. Side is equal to right. So this is the matrix you have got. And what was the earlier one? You can see this. Let us print both these together. You can see here both these matrices are same, right? So we can find using inbuilt function by restricting the domain and codomain, or we can use Rref. Both ways we will be able to find matrix of a linear transformation very easily. Okay, next let us look at how we can find, let us say, eigenvalues and eigenvectors, right? So we can simply say T dot eigenvalues. T dot eigenvalues. So the eigenvalues are 3, 2, minus 1, 1. So they are eigenvalues. And similarly, you could also find eigenvectors, right? So T dot, or you can find characteristic polynomial, T dot characteristic polynomial. You may have to mention with respect to which. So let us say with respect to X. So this is the characteristic polynomial. Okay. Now, how does one define eigenvalues of a linear transformation? One way is to find a matrix of T and find eigenvalues of that. So we have already found out matrix of T with respect to the standard basis. So for example, we already found out. So where was it? This is the matrix. So let me call that as A. I'll call this matrix with respect to standard basis as A. So let us say A is equal to matrix of T with respect to A. And when I say A dot eigenvalues, that is again 3, 2, minus 1, 1. But again the question is, if you change a basis, whether the eigenvalue will change. Okay, so let us find out. uh, uh, Let us of course, for eigen, since in this case V and W, T, if you want to define eigenvalue, eigenvector of a linear transformation, it has to be defined from space 2 itself. So domain and codomain should have the same basis. Okay, so let us look at, let me call this as T1 to be the restriction of T onto domain and codomain. Domain and codomain, let me just see. Domain and codomain, both restriction is V1. That means domain and codomain have a basis defined by D1 vectors D1, D2, D3, D4. Okay, right. And let us look at now what are eigenvalues of T1. T1 dot eigenvalues. First, T1 dot eigenvalues. Again we are getting same. Instead of restricting to D1, D2, D3, basis D1, D2, D3, now let us say we will take a basis C1, C2, C3. So that we have to restrict over W1, capital W1, and capital W2 here. Not, let me call this as T2. This is T2. So then again in this case, or you can take a random set of vectors, 4 vectors, look at a basis whether it is linearly independent, and then find eigenvalue with respect to that matrix. So this clearly says that the eigenvalues is independent, eigenvalue is independent of the basis, right? So why is that case? Of course you can check. Suppose I have called this matrix as A, and suppose let me call the matrix of T1, let us say as B. B is equal to T1 dot matrix side is equal to right, and then A and B have same eigenvalues. but this is because A and B are similar matrices. So let us check. A dot is underscore similar B. The answer is true. A and B are similar matrices, therefore they will have same eigen values. Okay, right. So this is how you can do various concepts related to linear transformation. It is very easy to define a linear transformation and find out various concepts related to that. Let me just do one more problem. This we have already done. Let us say we are given a linear transformation T from R3 to R3, which takes this basis 1 to minus 1 minus 1 1 1 1 minus 1 1 to a vector 2 1 1. So this is the first element of the basis. That image is the first element here, and image of this is second element here. Image of the third one is third element here. So this you are given a linear transformation image of a basis. So we know that a linear transformation is completely determined once we know how it is defined on a basis. Okay, right. So but suppose I want to find out what is this expression for this linear transformation. I want to know what is T of x, y, z. So what is the first coordinate? First coordinate will be some linear combination of x1 x, y, z. Second coordinate will be linear combination of x, y, z, and things like that. So we want to do this problem. Let us see how we will do. So first let me define these variables. Let us say x1 x2 x3, and we want to find out what is image of T of x1 T of x2 T of x1 x2 x3. Okay, so let me define. I can declare this variable. So let us say I call this as x as a variable. We can use var. We can also use symbolic variable sr dot var, and with the variable is x. And how many? Let us say we want 4 variables. So it will be x0 x1 x2 x3 x4. Right. So for example, if I say what is x is x0 x1 x2 x3 x4. Okay, so we will use these. Now what is given to us? So let us say, so we'll start with, let us say n is equal to 3, and in this case v is equal to w is equal to, let us say, q to the power n, that is 3, q to the power 3. Okay, now let us define these vectors as u1 u2 u3 as a basis vector, and its image as v1 v2 v3. Okay, so let me define that. Just 1 second. I'll just take it from somewhere. Okay, so u1 is this 1 1 minus 2, u2 is minus 1 1 1, and u3 is 1 minus 1 1, and you can check whether this is a subspace, this is a basis. It's quite easy to check. So and then I'm calling b as a v dot subspace spanned by this bd is basis for this domain u1 given by u1 u2 u3, and then next we will define the images v1 v2 v3. Let us define vectors v1 v2 v3, and the image is the list of v1 v2 v3. Okay, now let us define a linear transformation. So we'll call this as phi linear transformation, and it goes from domain v to w, and image we are going to, last time we mentioned f, that was the function. Now we will use image, EIMG. So let us say what is phi. Sorry, this phi. Phi is a vector space morphism represented by this matrix. Again, this matrix will be transpose of that, so you have to say matrix side equal to right. Okay, so this is the matrix you have got. This is a linear transformation. Now what is that we want to look for? We want to write this linear transformation. We want to know what is the expression, in the sense that what is each coordinate. So T of x1, T of x2, T of x3, how does it look like? So if I want to do what is t of x1, t of x2, t of x3, so for example, we want to say t of x1, x2, x3. So the first what we one way to do is x1 x vector x1 x2 x3 we can write as t of x1 times e1 plus x2 times e2 plus x3 times e3, right? Therefore t of x1 x2 x3 will be x1 times t of e1, x2 times t of e2, x3 times t of e3. So if I, but we already, in case we know what is t of e1, that we can find out, since we are given linear transformation t of e1 in Sage it will give. But if you want to find manually t of e1, you have to write e, since we t is defined on u1 u2 u3, therefore you have to find out the coordinate of e1 with respect to u1 u2 u3, similarly coordinate of u2 with respect to u1 u2 u3, and so on, right? So let us do that. So what we are going to get, we will, so let me again define E as identity matrix of size 3, and okay, so then let us say x x of I plus 1 times t of e I. Okay, so what is it going to give me? Let us say if I take I equal to 1, x of if I take I equal to 0, x of 1 is x1, and t of e1, that is the image of the first vector, plus t of okay, so this then I'll simply use for I in range n in this case, and then take a list of this, make a list of this, and then take a sum of these things. I think what does it say? There is some error. 10 failed to convert into map domain vectors. So I think T of EI is problem. Just let us see what is oh, we have not defined t, we have defined phi, so I have to say phi here, phi, yeah, right. So this is the expression for this linear transformation. First coordinate is 2x1 plus x2 plus x3, third coordinate is x1 plus x2 plus x3, fourth second coordinate is that, third coordinate is x1 plus x2 minus x3, right? And of course if you want, you can check whether this is same as, yeah. So let us say I want to define this as a for example, I'll define, let me say g of x1 x2 x3 is equal to a list, first coordinate is, second coordinate is this is, and now we want to define a linear transformation. Let me call this as psi is equal to linear transformation with domain V, codomain W, and the image is G, right? And you want to check whether psi is it equal to phi. The answer is true. So both these things you have verified that these two are one and the same thing, right? So of course you can explore other concepts in linear transformation. For example, you can look at when you change the basis on domain and codomain and what happens to the matrix. You can define the sum of two linear transformation. So for example, we already have two linear transformation. I'll say for example t1 and t2. So if I say t1 plus t2, it will give me the sum of two linear transformation, again is a linear transformation. You can also say t1 star t2. So this is composition of two linear transformations, and again you can find out matrix of the composition and verify that the matrix of composition is nothing but the product of the corresponding matrices. Okay, so that I leave it to you to explore, and of course I think it is there as one of the exercise in the assignment, right? Okay, Sage, using Sage you can also demonstrate geometric meaning of linear transformation, especially in 2 dimension and 3 dimension. So using Sage Interact. So let us say I have already written this code. So this is uh, what it does is it takes a 2 cross 2 matrix and some arbitrary vectors, 2 vectors, and looks at what happens to these vectors, how they are transformed under the given linear transformation given the matrix, and you can change that and automatically the images will change. So let me just 1 second. I think oh, this has got some problem. Let me start a new let me just look at this one. Yeah, okay. So so you can see here what is happening, how there is a matrix A is given in 2 cross 2 and vector u and v. So if I change, for example, if I take a diagonal matrix, this is diagonal matrix 1 comma 2 diagonal matrix, and then let me reduce the size so that you can see. So you can see here this blue color are the vectors in the domain, and the red color are the vectors in the codomain. So on x-axis it is extended uh, by on y coordinate it extends by 2. So that is why you can see here it is elongated by scale 2 along y-axis. If I change, for example, uh, this, let us make it this as 3, this as -1, then again you will see that it changes. So, and you can also change the vector. So instead of this I have 2 comma -2. Now this is different vectors, right? So using this Sage Interact, very easily you can explore this explain this geometric meaning of a linear transformation, and maybe you can extend these to 3 cross 3 matrices. So you'll have to instead of plot you have to use plot 3D, and this arrow 3D you have to use, and then line 3D, etc. You should be very easily able to convert this into 3 dimension. Okay, so and this is quite simple actually. It is, you don't have to, let me just simply explain what has been done in this case. It is fairly simple. So you simply take a matrix, you have to use of course Sage Interact. Let me explain it here. So you simply have to, just 1 second, you, let me make it slightly bigger so it will be, yeah. So all you have to do is at the rate interact, define whatever the function you want. So I have called here LT, take a matrix, right, and then take here u and v are also taken as a matrices, and then the using coordinates it is converted into vectors, but you can define as a matrix, and then you plot a u1 u v a u a v, and then join by that dotted line, and at the end, and of course you are adding some text that is label of the vector u a u v a v, etc., and then ultimately you just show this. Okay, so let me just what I will do is I will just copy paste here outside this interact. Okay, so let us see. I'll let me delete. So A is this, B, V is this. I have to remove this colon inner vector. Let me, okay, I have to remove these extra spaces. In Python it is thought of as indentation, so that is why you have to remove these things. Okay, still right. So this is the plot, and you can see that the same code is just put it inside the interact, so it is not very difficult. Okay, and you can now change whatever the vectors you want, whatever the matrices you want. Let me make it here 5, and then this is how the these vectors changes, right? Okay, so these are the things I wanted to cover, and mm, so in the next lecture, I'll do some applications of linear algebra, maybe 3-4 applications, which are quite nice applications, and you'll see that how we can very easily look at several applications of linear algebra using Sage. Okay, so thank you very much, and this worksheet along with the assignment will be posted on the app. So thanks again.